Hello Year 11, this is the Triple Science Physics Higher Paper 1 Masterclass. If you're not a Triple Science student and you're not doing the higher paper, you need to make sure you're opening the correct video or going to the correct room, because this is focused on the advanced information that we're getting. So it's not going to be as helpful to you as the correct video. Okay, now the triple paper is 100 marks and it lasts for 1 hour and 45 minutes. That should be about a mark a minute. That's what you want to pace yourself at. If you're spending too much time on a really short marked answer, in a short number of marks, don't waste that time. Put a star next to it, move on and come back to it and finish it. Okay, now the way this masterclass is going to work is that there are two colours of slides. With red slides like this one, that's where we're listening, where we're reading, and a lot of the time we're going to be fixing mistakes in past paper questions, common misconceptions, common mistakes that will drop you marks. So when it's red, we're reading and we're listening. When it's green, we're reflecting and we're writing. We're doing something active. A lot of the time it's going to be fixing that mistake, fixing the problem in that past paper question. So red, we're listening, we're reading, we're being quiet. Green, we're reflecting, we're writing. We might talk to the person next to you if it's relevant, if it's good, but that's when we're doing that. We're not doing that when the slides are red. Okay, here's the advanced information. Now your paper is going to have hopefully a heavy focus on energy. Okay, the big focus in this paper that we were told in the advanced information is energy changes, conservation of energy, energy transfers, internal energy and energy transfers, and then also changes of state in the particle model. Now there will be other content that will feature, but it won't be a focus on your questions. Okay, now you'll also have two required practicals that will be assessed in some way. We don't know how they're going to be skewed. We don't know if there will be only 1 or 2 marks on the thermal insulating properties of materials. We don't know if it will be a 10-mark question. We don't know if it will be equal, but we know in some way they will be assessed. So we're going to be going through those. So your first job, we've got a question on energy transfers. Okay, this question is at 6 marks and none of the marks have been scored. Now when you first see it, you might think, well, that looks actually, some of it looks true. And some of those answers are true, but they're not scoring marks. Okay, so you need to pause the video here and find and fix the mistakes. Okay, so moving on, we've got no marks gained, none. Okay, so using wood in a burning stove is a renewable biofuel. Biofuel because it used to be living, renewable because as soon as we burn some trees, we can plant some new trees and grow them again. Okay, and it will be replenished at the same rate we could use it. Now the environmental impacts, the fuel is eco-friendly, that might be true, but that's not detailed enough. We need to say why it's eco-friendly. Just saying eco-friendly is not enough to get the marks. Giving out pollution is not detailed enough to get the marks. What type of pollution? Okay, part C is a tricky part of the question. Describe the change to the stores of energy of the wood, pipe and water as the water is heated. The important word is change. So saying the wood, the chemical energy was transferred to heat, that's true. Chemical energy is transferred to heat when it's burnt. But that's not what the change is in that store of energy. Okay, so to get the marks, we need to write things like causes deforestation, gives out air pollution. Okay, smoke. For our changes, the chemical store decreases, thermal store increases. So whenever you see the word change in your paper, you need to think, is the thing going to go up, is it going to go down, or is it going to stay the same? You need to be really careful when you see that word change. Okay, next question is on specific heat capacity. You need to calculate the specific heat capacity of air. And we're given a balloon that's got the mass, it's got a temperature change, it's got an energy change. We need to use the correct equation on the equation sheet to calculate that specific heat capacity. You need to find the mistake, you need to fix it. Pause the video here. Okay, moving on. So, this mistake, we're not showing our math skills to a full extent. We need to make sure we substitute first. This student rearranged incorrectly, then substituted, and when they do it like that, you get no marks. So make sure you substitute first. Okay, if we substitute first, we're putting the numbers directly into where they need to be. We can go through each of our quantities. Now I like to put an underline, or I like to box those numbers when I'm reading the question. It helps draw my eye to when I substitute them in. So when I have the mass here, I know that the mass goes in the M for my equation. My temperature change goes in the temperature change in my equation, the delta theta. I know my energy change goes in my delta E, my change in energy. Okay, so I can rewrite this with the numbers instead. Okay, and then you didn't have to do the step. I like doing the step. We just simplify it a little bit to make it easier to rearrange, and then we can get the correct answer. Okay, and that will get you your 3 marks. So you need to make sure that you substitute first. Next question. Okay, next question is again on energy transfers. We've got a toaster. The toaster toasts some bread, and when it finishes, the toast is moved up by a spring. There's a change in gravitational potential energy. We've got a mass of the toast, and we've got a gravitational field strength. We need to calculate the change in height. Okay, so you need to make sure you fix the mistake. Pause the video here. Okay, so again, this student is incorrectly substituting. We need to substitute first. Like, we need to be really careful in what goes where. So in this case, we haven't put the quantities into the right spots. Okay, we need to be really careful that for energy, mass, gravitational field strength, and height, we're doing that correctly. Okay, so this time we substitute first. Okay, we're left with 0.049 equals 0.05 times by 9.8 times by height. We rearrange to find height. Okay, and we get an answer of 0.1 meters. Okay, you need to be really careful in really carefully laying out your maths. Okay, it will help you get all the marks. Okay, the other thing you want to be aware of is the height of the bread doesn't move up by a centimetre. Okay, that's unlikely. It's not really going to help you take the toast out of the toaster. Okay, moving up by 10 centimetres so you can properly catch it, okay, will be a little bit better. The next little tip is choosing the correct equation. Okay, now I think it's a good thing to do is to highlight or underline the quantities you're given. So in this question, it was gravitational potential energy, mass, gravitational field strength, and height. Go through the equation sheet until you find the equation with all of those things. Okay, use the correct equations. Okay, that's going to be half the battle in getting your maths marks. Picking the correct equation will help you gain those marks. Okay, take advantage of this. The following years aren't going to get this equation sheet. They're going to have to remember all these equations. Okay, so take advantage. Okay, make sure you match up the quantities to the correct equation in the sheet. Next, we've got a question on energy transfer in terms of heat. We've got a bowl that we're using to make ice cream. We've got liquid coolant inside it. The inner surface is metal, the outer surface is plastic, and we've got this mixture that we're going to make ice cream with. Okay, and the question is, explain why the different thermal conductivities of the metal and plastic are important in the design of the bowl. Okay, it's 4 marks. Okay, that means there's going to be 2 marks for metal, 2 marks for plastic. Okay, really carefully read what the question is asking and then try and get the 4 marks. Find the mistakes. Pause the video here. Okay, moving on. Okay, the metal is a poor insulator. Okay, I don't care about insulation in this question. I care about thermal conductivity. Okay, to get the marks, you have to talk about the properties of the material in terms of its thermal conductivity. Is it a good thermal conductor or a poor thermal conductor? Okay, so you need to say that metal has a high thermal conductivity. This increased the rate of energy transfer from the ice cream, so it will get colder quicker. Okay, plastic has a low thermal conductivity. This reduces the rate of energy transfer to the surroundings, so our liquid coolant doesn't warm up quickly. Okay, but the key thing is, in the question it says, explain why the different thermal conductivities of the metal are important. Use that language in your answer. You have to use the idea of thermal conductivity to get the marks. Okay, now this is highly related to our required practical. Okay, so our first required practical is on insulation, and the thermal conductivity is a different insulation. So we've got a simple setup here. We've got a thermometer, large beaker, small beaker. We've got a piece of card. We've got a stopwatch. Okay, I've got a really brief method. I'd like you to try and improve that method. Put more detail into it. Okay, I've got a graph here showing different materials. So material 1, 2, 3, 4, and then a control with no insulation. Okay, which material has the lowest and how can we tell? Okay, how can you improve this experiment? How would it change if we used iced water, so water at 0 degrees, instead of hot water at 100 degrees. Okay, how could you stay safe? What's the risks involved in this practical? Okay, so pause the video here, try and improve on our method. Okay, moving on. Okay, so this experiment I don't think is too difficult an experiment. I think we've been really lucky in triple that it's a relatively straightforward experiment. Okay, we need to be aware of the different parts of the kit. So thinking about why we'd use this large beaker, it's important to insulate from the surroundings so don't get extra heat loss. Okay, we need to be aware that eventually all of these temperatures will reach room temperature. They'll get to thermal equilibrium with the room they are in. Okay, we need to be aware of why there is a temperature change. When this fluid, when this material is hotter than the surroundings, it will transfer heat to the colder area. That always happens. Okay, so if we were to use cold water here, if it was at freezing, the temperature would rise until it hits room temperature. Okay, so the graphs would look different. Okay, when you're writing your method, if you need to write a method, state exactly and explicitly each piece of equipment you would use and what you would use it for. So what would we use the thermometer to do? We measure with the thermometer. Okay, make sure you're really explicit in how you use the equipment. Okay, next slide, we've got density. Okay, I'd like you to draw a diagram of how you would use a displacement can to calculate the volume and therefore the density of an irregular shape. I'd like you to try and finish and fill in our method for calculating density. I'd like you to try and write down the units that we could use for density, mass and for volume. And I'd like you to try and calculate the density of this 50-gram rock that displaces 30 centimeters of water in kilograms per meter cubed. Okay, you can also get it in grams per centimeters cubed, but I'd like it in kilograms and per meter cubed as well. Be very careful about your conversion of centimeters cubed into meters cubed. Okay, pause the video here. Okay, moving on. So our displacement can, we put our irregular object into it. Water will flow out through the top of the displacement can that we catch in a measuring cylinder, and that volume of displaced water equals the volume of the irregular object. We could also just use the measuring cylinder. Okay, so we can add a quantity of fluid into the measuring cylinder, we could add our irregular shaped object, and the volume that we read will increase by the volume of that irregular object. Okay, we use a mass balance to find the mass, then we can use our formula to calculate its density. Okay, now we tend to use the unit of grams or kilograms for mass, and centimeters cubed or meters cubed for volume. Both are used when we're using the density equation. Now, the better unit would be meters cubed and kilograms, but because generally speaking when we do this experiment we use quite small things, it will be very small when we use that as a number. Okay, so be aware that you might get different units in these questions. Okay, here's my method. My missing bullet point was measured the volume by placing the object in a displacement can and measured the displaced water using that measuring cylinder. Be explicit in what equipment you use. Okay, now when we're doing our calculation, okay, we need to be really careful about the difference between centimeters cubed and meters cubed. There are 100 centimeters in a meter, but there are not 100 centimeters cubed in a meters cubed. Okay, so we want to convert it into meters cubed. We can do 30 divided by 100 cubed. Okay, so our volume in meters cubed would be 3 times 10 to the minus 5. So our density is 1,733.3 kilograms per meters cubed. Okay, so be careful with that conversion. Next slide is about pressure. We've got an air canister. Okay, and it was tested to find out how the pressure changed when it was used by a diver. Okay, so this is the time in minutes and this is the pressure as it changed throughout the dive. Okay, it was measured every 5 minutes for 80 minutes. You need to estimate the atmospheric pressure using this graph. Divers can stay safely under the water when it's got to 25% of its original value. How long does that take to get to it? What would happen to the volume of air when it's released from the canister? Okay, so I've got my answers here. You need to find the mistakes and correct them. Okay, not all of these answers are incorrect. You need to find the mistake. Pause the video here. Okay, so the most obvious thing, the biggest mistake, okay, because the atmospheric pressure question, that is correct. Atmospheric pressure is 0.1. That's the level it gets to at the bottom, that equilibrium level when it doesn't decrease anymore. Okay, that's correct. But here we haven't used a ruler to move along in our graph, and we haven't read our graph correctly. It does not start at 2.5. We don't find out what a quarter of 2.5 is. We find out what a quarter of this value is. Okay, this is 2.25. Okay, so once we've found that and we found a quarter of that, we move along down the graph and it goes down to about 25 to 28 minutes. Okay, now because you're using this on a screen, you've got a little bit more leeway in getting the correct answer here. You'll have a little bit of benefit of the doubt in terms of your graph reading. It will be easier when you've got the actual paper in front of you. Okay, right, moving on. Why did this student only get 2 marks? They're doing pull-ups, lifting the body 0.4 meters vertically up. Okay, the mass of the student is 65 kilograms. The student's able to do 12 chin-ups in 60 seconds. Gravitational field strength is 10 newtons per kilogram. Using the correct equation on the equation sheet, calculate that power. Why did the student only get 2 marks? Pause the video here, fix their mistake. Okay, so the student, okay, didn't read the question properly. They skipped past this part where they're doing 12 chin-ups. So we've correctly calculated the energy of 1 pull-up, okay, 1 chin-up. They didn't then times that by the number of chin-ups they did. So 260 times by 12, this 3,120 is the total energy over those 60 seconds. Then we can divide it by 60 to get a power of 52 watts. Okay, so be really careful. This is the kind of problem that you can easily attempt. You can see and go, oh, I know how to do this. And then you just lose sight of the extra bit of the question. Okay, and we know that because it's 3 marks. We're given the unit, so we need to do something else apart from just substitute and get the answer out. Okay, we need to be really careful. Next, why did the student only get 1 mark? The energy transferred from water to the kettle and the surroundings in 2 hours is 46,200 joules. Calculate the average power output from the water in the kettle to the surroundings in 2 hours. Use the correct equation from the physics sheet. Okay, so why did the student only get a single mark? Find the mistake, fix it. Pause the video here. Okay, so this student didn't fully change our 2 hours into seconds. We changed it into minutes, but not into seconds. So we need to times 2 by 60, then times it by 60 again to get 7,200 seconds. We always want to work in seconds when we're calculating power. Okay, be really careful of the units. At some point in this test, you will have to convert units. If you miss that, if you get to the end of your paper and you haven't done any unit conversions, you've missed it. Go through the paper and find where that is and do that unit transfer. Okay, don't miss that mark. Next, what equations will you use? Why can you not just use one? We've got an initial temperature of a mixture with 20 degrees. The mixture froze at minus 1.5 degrees. A total of 165 kilojoules of internal energy was transferred from the mixture to cool and freeze it. The specific capacity of the mixture is 3,500 joules per kilogram. The latent heat of fusion of the mixture was 255,000 joules per kilogram. Calculate the mass of the mixture. Give your answer to 2 significant figures. Okay, what equation will you use? Why can you not use just one? Look at the marks. If it's a 6 mark or a 5 mark calculation question, you are going to have to use more than one equation. In this case, you have to use 2 equations. Okay, so pause the video here and try and calculate the mass of the mixture. Pause the video here. Okay, now this question is a difficult question. This is as hard as specific capacity gets. Okay, this is difficult. Okay, now the reason why we need to use 2 equations is energy is used for both changing the temperature and changing the state. So we need to use the change in energy equals mass times specific capacity times by change in temperature. and energy equals mass times latent heat. We can put those two things together for the total energy, the energy required to change the temperature and the energy required to change the state. We can substitute in our answer into our numbers into our equation. We can simplify. We can then rearrange, and we can get an answer of 0.499621 kilograms. We can then round that to two significant figures, so 0.5. Now, if you get to a question like this and you're finding it really difficult, don't just give up. Don't leave it blank. Put something. There's lots of marks to be gained in these long calculation questions from some correct usage. Okay, this is only part of the mark scheme for this question. There are lots of marks you can get even if you don't get the correct answer. Okay, especially if it's got a significant figures, you might be able to get a mark for just converting your answer into the correct number of significant figures. Okay, so don't lose marks for thinking that it's too hard and you should just give up. Give these long calculation questions a go. Okay, let's have another one. We've got the power of a kettle was 2.6 kilowatts. The kettle took 120 seconds to heat 0.8 kilograms of water from 18 to 100 degrees. Calculate the specific heat capacity of water using this information. Give your answer to two significant figures. Okay, what equations will be needed? Pause the video here, give this question a go. Okay, so difficult question, again, 6 marks, we need two equations. We're also putting our answer to two significant figures. Okay, so the equations we need are going to be energy equals power times time, and change in energy equals mass times specific capacity times by change in temperature. So we can first work out the total energy because we know the power and we know the time taken. We times those things together to get the energy. Okay, that will give us 2 marks on its own. We can then substitute it into our specific heat capacity equation using our change in temperature from 100 to 18. So change in temperature is 82. We rearrange this equation to find specific heat capacity. We get a specific heat capacity of 4,756. We then put that as two significant figures, so 4,800. Okay, give these questions a go. There are lots of marks you can get even if you don't get the right final answer. Okay, next we've got another multi-equation question. This one we've got water vapor condensating onto a glass, onto a cold mirror. Okay, we've got a very small volume, a volume of 2.5 times by 10 to the minus 5 meters cubed of condensation. Okay, the density of water is 1,000 kilograms per meter cubed. The specific latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. Calculate the energy released when condensation forms. Okay, it's a 5-mark question. That means we need 2 equations. We need the density equation and the latent heat equation. Pause the video here, see if you can get the answers correct. And moving on. So here we need to first calculate the mass. We know what the density is. Okay, we know what the volume is. We can find out what the mass is. Okay, we write the equation, we substitute it, we get a mass of 0.025 kilograms. Okay, we then can use energy equals mass times latent heat capacity, and that allows us to get an energy value of 56,500 joules. Okay, we need to be careful in substituting into the correct equation first. It helps if we go through the equation sheet and look at all the equations we could possibly use. Okay, now that's the last slide we've got. Okay, if we've got any remaining time, I would suggest practicing some of the skills we've looked at in this unit and doing your own focused revision on any of the past paper questions that you've got with you and that your teachers can use. Okay, well done Year 11, you can absolutely smash the paper. And I'm looking forward to see and hear what you think about it afterwards. Good luck.